This is a second video on Euler's totient number. Okay, so if you didn't watch part 1 on this topic, please watch it, because part 2 is just a continuation of part 1. Okay, now the conclusion of part 1 was that we were going to consider a natural number n that's not 0, and we are going to look at sets of numbers like so, from 1 to n, okay, from n plus 1 to 2n, and from k minus 1 times n plus 1 all the way up to kn. Okay, what's special about these sets of numbers? The last number in every single one of these sets is a multiple of n. Okay, and every single one of these sets has n many elements in it. Okay, now recalling the definition of Euler's totient number, so here we have phi of n many numbers that are relatively prime with n. Now the question was, are we going to have in here phi of n many? Are we going to have in here phi of n many? Okay, so this was the claim that we were going to discuss based off of our discussion in part 1 of this video. All right, so now, okay, here's what we can do. So we can start off with some natural number. That can be in here, that can be in here, it can be in here. Okay, clearly it's going to be in one of these batches, because these batches of numbers, these sets of numbers, will actually partition the set of natural numbers. Okay, so now, okay, really what's given to us is this natural number n. So it's kind of normal to look at the division of x divided by n. So let's say x is q times n plus a remainder of r. Okay, now what this simple operation will do is we'll take some x that's somewhere in here, and we'll associate this remainder of this division. Okay, okay, so fine, we can say, oh, well, hold on, but this remainder can be 0. Yes, the remainder can be 0, but if the remainder is 0, so if this number disappears in here, our x is just a multiple of n, so it has no hope of actually being a number that's relatively prime with n, so that doesn't bother us really. Okay, so here's what we're going to do. If we say that if d1 is the greatest common divisor between n and r, okay, well, let's look at what's happening here. So let me copy this again. So x is q times n plus r. Okay, so again, d1 is the GCD between n and r. So d1 appears in here and it appears in here. So, well, we don't know the value of it, but we know that we can factor it. Okay, so this is going to be d1 times, okay, so it's going to be something left from this number plus something left from this number. There's no point in actually us, sort of writing down what's left from these numbers. Okay, it's not a perfectly written proof, but I want to get the message across. Okay, so we're going to have a number here. Okay, I'm just going to write these dots here. So we're going to have a natural number. So x is d1 times this natural number, which means actually that d1 divides x. All right, so now d1 divides x. d1 also divides n, right? So d1 also divides n, okay, which means that d1 is a divisor of the greatest common divisor of these two numbers, is a divisor of the GCD between n and x. All right, it's interesting. Okay, so let's put this into a box, because this is an interesting relationship that we got. All right, now let's say if d2, okay, we can say let d2 is the GCD of n and x. All right, well, if we look back at this relationship here, how about we move the qn over to the other side? So we get r is equal to x minus q times n. Okay, and then again, look, d2 divides x, right? Also d2 divides n. So in between x and n here, okay, so over to the right hand side, we can factor a d2. So it's D2, and we know we are going to have a nice leftover from X and minus a nice leftover from Q times N. So again, we are going to get a nice natural number, okay? Which means that D2, right? D2 will divide R. All right? So D2 divides R. D2 also divides N. That's how D2 was chosen. So that means that D2 divides the greatest common divisor, GCD, between N and R. Well, okay, so this is the second relationship we got. Okay, well, how can we put these two together? Actually, this means that D1, right? D1 divides GCD between N and X. Well, eventually we gave this a name, so this is our D2. And then here we got D2 divides GCD between N and R. Well, this is just D1. Well, so D1 divides D2 and D2 divides D1. So that tells us, okay, so that tells us that D1 is actually equal to D2. Very nice. Okay, so basically, the greatest common divisor between N and X is the same as the greatest common divisor between N and R. Right? So now we are looking for, actually, in order to get a better understanding of this totient number, we want the greatest common divisor between N and R to be 1. All right? So basically, in here, every single number you take from here that's relatively prime with N, subtract N from it, and you get another number that's going to be in here that's relatively prime with N. So indeed, we do get 5n many numbers in here. All right? And the same is true with the following sets of numbers that we consider here. We are going to have 5n many numbers that are relatively prime in every single one of these sets, and actually they're very nicely distributed. Actually the pattern that we kind of saw in the previous video on this topic will keep being a valid pattern in this general setup. Okay, so the numbers we are going to have here between 1 and n, we are going to have 5n many numbers that are relatively prime with n. In between n plus 1 and 2n, we are going to have 5n many that are relatively prime with n, and so on and so forth. And they are going to be distributed in a very, very nice pattern. So the claim that we came up with from part 1 of this series is actually true.